Oh, it didn't go. So, thank you. First, I'd like to say it's been a great privilege for me to be here these days and hear all the wonderful talks. And now I have one more privilege, and that's to talk. So thanks to the Newton Institute. And I apologize for the broken record in the title here. But anyway, in short, what I'm going to try to tell you today is what can we learn by looking at DNA in the simplest possible way and still learn something? Or rather, what can we get from looking at DNA in the simplest possible way and therefore learn something new, of course. And this is work done together with Kasper Olsen, my co-worker here. And this is a model of collagen, which also has a story, but we will get to that in the question session. So the first slide here shows the nucleosome. And the nucleosome is just the first level of compaction of DNA. It's, maybe this is dangerous, but you wrap around the double helix around some proteins here. And the question is, you do this twice, and you can see it's almost a Torus link if it has closed up. So we will get to that in a minute. But the first question we want to address is a biological question. Why is the diameter of this nucleosome the same in all the eukaryotes, which for example includes mammals and plants and everything? Well, not everything, but why is there no evolutional pressure that the bottle of water there, the proteins, would grow in some branch of life and not in other branches? So presumably there's some principle behind that. There's a principle for winding that helps us, probably some physical principle, which I'm going to get into. But before I can explore that, I need to know what is the principle for holding DNA together on the short length scale. Not just the coincidence of the base pairs, but on a physical thing. So we look briefly at helixes. The DNA is a double helix, and as you can see here, the diameter of the packed double helix changes with geometry. That's all you need to get from this slide. So that's what I have here. The diameter, if I have a pitch angle down to 45 degrees, then the diameter is constant, and then it begins to increase because I get a large helix. That allows me to calculate a volume fraction. So I have to do that a little bit more slowly. I'm a little bit scared about the timing, we don't have a pointer. So the volume fraction here, it goes up as I wind the helix down in pitch angles here, down to 45 degrees. But then you can see that it continues to go up here, and it's just a question of what's the ratio of the space used by the strands to the ratio of the overall space used. Just as we know from close packing of spheres and other things. O'Hara has similar results as the one I've shown here on the view graph. But the essential thing is to take out is that there is a maximum. So it would be natural for nature to have used this maximum. Can I just go down here? Yes. And that's what you see here. The maximum here corresponds to DNA A. And this curve here is for DNA B, which is an asymmetry called the double helix, and the maximum, close to the maximum, corresponds to the maximum. We get approximately ratios of 1, within 2 parts in 1,000 away from 1, just from this very simple helix model. So that means that now I have a packing principle, even that I have this simple tube model that I can use for my nucleosome locally. So that's just to remind you that it's common and ubiquitous in nature to have close pack. Even candy is close packing. And quartz crystals are also close packed if you calculate it, at least some of them. So we now have our local principle here, that we get the local density from close packing. What happens if we, instead of looking at the ratio of the volume, looks at the ratio of how much the two are rotated around each other, so to say, the progression of winding of the two strands relative to each other. That would give us a minimum of rope length, for example, which is a different criteria. So let's see what happens. And interestingly, here I have the pitch angle here, and here I have this progression of the winding of the two strands relative to each other, and you see that of course it goes through a maximum. So this is the maximum rotated structure, or the ones that has the shortest rope length. So it's a different one from before. DNA is known to overwind. This was shown in two experiments in 2006, Lionet and Bohr, both et al. And what they mean by that is simply that when you pull DNA, stretch it, instead of untwisting the two strands relative to each other, they actually wind additional around. And if you go back and look at this, it's kind of a trivial that it has to be this way. On the one side here, you wind more when you strain it. On the other side, you unwind. So no peculiarity in that. It's just that comes general from this. And you see here, I have them about here. This is the one with the shortest rope length that does nothing. This is where DNA is, and this is a 45 degree. But the interesting question to get to the nucleosome is, what happens when we bend the helices? And that's what's shown over here, that we now have these two measures, local optimum packing and the global shortest rope length here. And you see that as we bend them here, they meet. And so we want to explore this to further details. This is just to confirm that we can calculate the base pairs per DNA. I haven't shown the base pairs, so I haven't made any discretization before now. But now I can make a discretization, and this is a result that the curved DNA has about 10 base pairs per 2 pi rather than 10.5. That was already predicted in 1978 by Levitt. It's at Stanford. Here's the nucleosome. What we get is that if we require that we have this twist neutrality, which corresponds to that when we pull in it, that there's no rotation, neither right nor wrong, nor left. Then we get to there is an arrow. Then we get to a criterion of 82 angstrom, and the crystal structure is 84 angstrom. So that's pretty close, and that's closer to than the accuracy of the method. So that's just a summary that we can explain the requirement for DNA to behave well under stress. You have to think about it in the way that when you do transcription, you would like to unwind this thing locally, while it is still connected as a long double helix. So you don't want it to do long rotations or massive rotations. Let's look at the Torus knots and Torus links. The one we had before was the DNA likes to make. One could think of this as a small plasmid, which would be a link. So both of them comes out of the calculation. So you can do the same thing again. Look at the incremental winding of the one relative to the other, estimate the rope length, and as long as you preserve the symmetry, the Torus symmetry, you don't need any knot tightening algorithm to estimate the rope length. So just go there. And I know we're pretty late, so I would like to thank you for your attention. That's fine. Yes.
Questions?
So
So I'm just curious, it was really interesting, the bit on the nucleosome. So are you saying just using your close packing algorithm that you get the diameter, the histone diameter, out for the wrapping?
It's a combination of two things. It's requiring that it's locally is close packed. That means that it's locally has optimized the volume fraction. And globally, if you put it in the one end, you put it on the 10th strength, that it doesn't rotate.
Questions? Okay, we should thank all our speakers.